Thank you. So I'm doing a postdoc at the moment at the Karlsruhe Institute of Technology. However, the work I'm presenting here was done during my postdoc stay at Argonne National Laboratory. And let me take a moment in the beginning to acknowledge my collaborators there. So most of the experimental work has been actually done in close collaboration with the postdoc there, Matt Smiley, under the supervision of Ulrich Werb. The crystals that we had at the time came from Brookhaven National Laboratory. The proton irradiation that we have done was done at Western Michigan University. And we were in close contact with Andreas Ried from Stockholm University for the specific heat measurement setup that I built there. Now, funding for the work at Argonne usually comes from the Department of Energy. My research stay has been funded by the Swiss National Science Foundation by a postdoc mobility fellowship, and my current stay at KIT is funded by the Alexander von Humboldt Foundation. Okay, so doped bismuth selenide. So as you might know, bismuth selenide is a topological insulator. Let me start by introducing this one. So a topological insulator, in contrast to a band insulator, where we have the Fermi level and the band gap between the bulk and the conduction bands and no states available for conduction, has, due to strong spin-orbit coupling, this band inversion, which leads to a crossing of the bands at the Fermi energy, and thus makes surface states available on the surface for conduction. Those surface states are symmetry protected, they are spin momentum locked, and thus not very easily affected by scattering. Now, with the theoretical concept of a topological insulator also came the theoretical concept of a topological superconductor, which was very early on discussed for several one or two dimensional systems. And people realized that in these systems, due to the topological nature of the system itself, it's actually possible to have so-called Majorana states in either vortex cores or in the edge states of these systems that would be also symmetry protected and free from decoherence, and thus have the possibility to allow for quantum computing. Now, while those systems were discussed theoretically, only with the discovery of a real bulk topological insulator also came the realization on how to actually make a topological superconductor. And there are actually two possibilities to do that. So one is by the proximity effect. We could deposit an S-wave superconductor on top of a topological insulator and thus induce superconductivity here. The other way is by doping the bulk of the topological insulator, thus making it superconducting, and have topological surface states here as well. So I'm going to talk about the second possibility, and the topological insulator of our choice will be bismuth selenide. Let me quickly introduce this compound to you. So bismuth selenide has a trigonal crystal structure, which naturally leads to a six-fold symmetry in the crystal plane. It's composed of quintuple layers of bismuth and selenium stacked on top of each other, and those layers are actually separated only by a weak van der Waals gap, making it thus easy to intercalate doping ions. And as I have said in the beginning, the doping that we will be looking at will be done by copper, niobium, or strontium. Now, for the in-plane symmetry, there are two axes in the system very important. There's the A-axis and the A-star axis in this trigonal crystal structure. And I already want to point out there's a clear distinct difference between those two, namely that for the A-axis itself is no mirror symmetry, is not a mirror axis in the system, whereas the A-star axis actually, as you can see here, is a mirror axis. We will need this later on. Now, as I said, we can dope the system, and it has been discovered actually the first time with copper doping that if you do about 10% copper doping in bismuth selenide, the system becomes superconducting. You can see the very first measurements of magnetization and resistivity here. The superconducting transition temperature is about 3 Kelvin. And also very nicely done shortly afterwards were APIS data, where we actually see that with the doping, we of course induce charge carriers. We thus raise the Fermi level from this band gap into the conduction bands, having the charge carriers now available for superconductivity. But however, also luckily, we do preserve the spin momentum locked surface states that we have from the topological insulator. So we do preserve the topological nature of our material. Now, doping has been also achieved with niobium and strontium pretty shortly afterwards, and they all show the TC in about the same range, around 3 Kelvin. Now, also very shortly afterwards came the first measurements that showed a very peculiar feature of these systems, namely that if you look at the in-plane anisotropy, and despite the trigonal crystal structure, we actually see a clear twofold anisotropy in the plane. This has been done in seen in various different measurements, namely in copper-doped bismuth selenide and the NMR night shift. We can see it in resistivity measurements for strontium-doped bismuth selenide or in magnetic torque measurements for niobium-doped bismuth selenide. Now, after the first reports, actually before the first reports of these twofold anisotropy were published, theorists were very quick in telling us that the underlying superconducting gap structure could be at the origin of this, and they termed this nematic superconductivity, as the trigonal crystal structure of the crystal is broken into a twofold one. However, of course, we would have to think about possible conventional sources or external parameters that could lead to such an observation. So in the following 20 minutes of my talk, I want to first show you the evidence that we have collected at Argonne for this twofold rotational symmetry breaking. I want to quickly spend 1 or 2 minutes on showing why we do not think that conventional sources are responsible for this twofold symmetry breaking. And then I want to discuss a bit on why we think the superconducting gap structure is at the origin of this and which superconducting gap structure will actually be realized in this system. And in the end, I want to discuss a bit about the nematic direction in these systems. Okay, so as most of my measurements are done in specific heat, I want to start with introducing you to the setup that I was using at Argonne. So the specific heat setup that I built there is based on silicon nitride membranes. That means we take a silicon wafer, we coat it with silicon nitride. The silicon itself is later back-etched, leaving only 150 nanometers thin transparent membrane here suspended over a 1 millimeter square window. The active layers that we need for specific heat measurements are then deposited by photolithography in the center of the membrane. You can see a microscopic image here. And since we're using the AC specific heat technique, what we actually need is an AC heater, which subjects our sample to an oscillatory heat current, and we then pick up the second harmonic response of the sample via a thermometer. The offset heater here is used for regulating the overall temperature of our sample. So since the thin membrane has a very low superconductivity, it actually decouples our sample from the environment, and as it itself also has a very low heat capacity, it adds a very low addenda to our measured specific heat. And with this, we are actually able to measure very small samples, easily smaller than 50 by 50 by 10 micrometer or microgram in size, to a very high resolution. Okay, and the first samples we actually wanted to measure with this setup was the specific heat of strontium-doped bismuth selenide. Why that? Well, actually because it has been the specific heat of niobium bismuth selenide and copper-doped bismuth selenide had been published very early on, showing nice specific heat jumps at the superconducting transition. However, for strontium-doped bismuth selenide, specific heat had been published without the mention of any superconducting transition, which you would naturally expect for a superconductor. So we set out to measure this compound, and you can see here the first measurement that we conducted on the left-hand side, a cool down from room temperature, and then a zoom in into the superconducting region. And as you can clearly see here, I guess there is not much superconductivity to be seen. It took us a few samples to realize, but if you actually measure the 1 Tesla curve, which suppresses superconductivity and makes the sample normal, and then you take the difference, due to the high resolution capability of our setup, we were actually able to resolve the superconducting heat jump in the sample, which is less than 0.5% of the specific heat at that temperature, or 0.27 millijoule per mole Kelvin squared. Of course, this is a very tiny specific heat jump compared to other superconductors that we know, and you might naturally ask whether this is actually bulk superconductivity. And we are pretty confident that it is the case for many reasons. However, I'm just going to give you a quick argument here, namely the specific heat of copper-doped bismuth selenide, as I told you, has been measured before. it shows a specific heat jump that is about a factor of 10 larger than the one at strontium-doped bismuth selenide. However, also the carrier concentration, this compound is about a factor of 10 larger. So we think this small jump is mostly due to the low carrier concentration in our material. So having measured that jump, of course, we also wanted to see whether we also see is this twofold anisotropy in the plane. And in order to do this, we apply a field of 0.4 Tesla in the crystallographic plane. And we measure a temperature sweep through the superconducting transition, which is naturally suppressed by the field. However, when you start rotating the field, you will see that the suppression is much smaller as the angle of the field moves in the plane. So now there's two ways of looking at this. So we could either take cuts for constant temperatures through these different field angle sweeps. And I'm plotting this here on the right. So you can see here the in-plane field angle and the specific heat for different temperatures. So what you see here for high temperatures above the superconducting transition, the specific heat is essentially constant. Whereas once we start entering the superconducting transition, we see a clear twofold anisotropy of the specific heat emerging. You can also look at it differently. You can also take the superconducting transition temperature. Here it's simply done by the midpoint of the transition. And you plot this as the function of field angle. And also here, you can see for the full rotation of the field on the plane, you see this nice twofold anisotropy. Now, as has been pointed out by previous studies, and I will come to the assignment later, but just to make the assignment clear here, so we will call the maximum here of the TC along the a-axis and the minimum along the a-star axis. Now, of course, you can also then, once you have these maximum and minimum axes, you can extract the phase boundary for the system, and you can plot here for the a-star axis and here for the a-axis the upper critical fields, and also here you clearly see this rather large anisotropy of something between 3 and 4. Now we've done similar measurements for niobium-doped bismuth selenide. Here, since the specific heat jump is much larger than in the strontium-doped compound, we can already start to see this twofold anisotropy by taking a very small field of about 50 millitesla and just monitor the specific heat for a constant temperature at about the superconducting transition, and you clearly see this twofold anisotropy when the field rotates in the plane. We've actually even extracted the full three-dimensional plot of the specific heat also for a field of 50 millitesla rotating in 3 dimensions in our triple-axis cryostat. And while you see a clear, of course, a clear in to out of plane anisotropy, you also clearly see a twofold anisotropy in the plane with this dark shaded region here and this light green region there for the two 90-degree different axes in the plane. Also here, you can see it if you extract the phase boundary. There's a maximum and a minimum in plane upper critical field. Now a third proof for this twofold anisotropy comes from transport measurements. And here you see transport measurements for strontium-doped bismuth selenide, the cool down from room temperature, and to zoom into the superconducting region. And also here, what is very nice for transport measurements, as they're very sensitive, you can apply a field of 1 Tesla in the plane. And then what you do, you stay at a constant temperature, you rotate the field, and you get these nice color-coded maps here. So the red curves are for higher temperatures, and you can clearly see that as long as the temperature is so high that we are above the superconducting transition, the sample is normal and there is no anisotropy of the resistance. However, once we start going into the superconducting state, there are regions for the field where the sample is still normal, whereas there are other regions where for that temperature the sample is already superconducting, and this shows this clear twofold anisotropy. Now, I promised you to exclude some of the conventional sources that could be at the origin of this. Well, the ones we could come up with and that we've investigated is that you could think there might be some effective mass anisotropy in the plane. However, this would also show in resistivity, since the mass anisotropy can be related to the ratio of the resistivities along the 2 different crystallographic directions. We've done the measurements on one crystal, and you can see that there is not much difference between the 2 crystallographic directions. We actually attribute this more to a geometric normalization issue. So A second thing that you could think is that there could be some magnetic anisotropy in the sample. So we've done susceptibility measurements, which also show no difference for different crystallographic directions. And the third option, that there could be structural distortions already present in the crystal. We've done X-ray diffraction measurements at room temperature, which do not show any deviation from the trigonal crystal structure. You can see here the Bragg peaks at the positions where they should be expected. Now, another thing that came up is whether it could be due to the crystal shape, the vortex motion that is induced by the current flow, or misalignment of the magnetic field in the plane. And we wanted to come up with an experiment that could disprove this. And what we've done is the following. So we took a large crystal of strontium-doped bismuth selenide. We cut 2 crystals out from it, which has about the same shape ratio. And we put at a 90-degree angle, and we positioned those next to each other on the same substrate. So they have the same current direction, the same shape, and they will have the same field on the cryostat. And we've done transport samples, so we could monitor this, these shapes here for constant temperature field sweeps in the plane. And also you can directly see that those are not pointing in the same direction, and we thus exclude those things here being responsible for this anisotropy. So, well, if there is no conventional sources, well, let's consider the series option of the superconducting gap structure. Well, there are several superconducting gaps that are possible for this trigonal system. There are the one-component order parameters that are labeled delta 1, delta 2, and delta 3. And there are the two-component ones, delta 4x and delta 4y, which are allowed for our system. Now, you can immediately see that delta 1, delta 2, and delta 3 do not have any in-plane anisotropy, so they couldn't be responsible for the twofold symmetry that we see. However, delta 4x and delta 4y have a clear twofold anisotropy in the plane, so they could very well explain our observations. How can we distinguish between those two? So delta 4x actually has a point node that is along the ky direction, which corresponds to our A star crystallographic direction. And it's a point node that is symmetry protected, as I have told you before, that this is a symmetry axis in our system. In the case of the delta 4y, we actually have a gap minimum along the kx direction, which is a minimum because it's not symmetry protected, as it's along the a-axis, which is not a symmetry axis in our system. So those two would actually explain the nematic superconductivity that we are seeing in our system. So how can we tell whether one of the two, or which one of the two is realized in our system? And I will show you two experiments regarding this. So the first one is actually the same transport measurement that we have done before. However, and now we've oriented our crystal beforehand with X-ray diffraction so that we know which way the A-axis and the A-star axis in our crystal, in our transport sample, are actually pointing. And if we apply a field of 1 Tesla along the A-axis or the A-star axis, we actually see which one has the maximum HC2 and which one has the minimum HC2. And obviously, the one which has the minimum HC2 also has to have the minimum in the superconducting gap structure. And this one has to have the larger gap. So you can also, of course, then do the full sweep in the plane. And you can have here the axis is indicated. So again, the minimum in resistance is the maximum in HC2, or the maximum in the gap function. And the maximum in resistance is the minimum in HC2 and also the minimum in the gap. So this would be clear evidence for the delta 4x realized in this sample. Well, you can, of course, you can orient your crystal and you can measure the upper critical field. However, it would be nice to have some more direct evidence of which gap is actually realized in our system. And for this, there's a certain technique which is very well suited for that, and this is TDO, so tunnel diode oscillator measurements. Tunnel diode oscillator measurements measure the penetration depths of a superconductor, and by the low temperature behavior of the penetration depths, we're actually able to say something about the superconducting gap structure. Now, I will just tell you this here. So for point nodes, as it was the case in the delta 4x gap structure, we would expect the penetration depth dependence of t squared, whether for a fully gapped superconducting order parameter, we would expect to see some exponential low temperature behavior of the penetration depths. There's a small problem here, and that is if the temperature that is accessible in our experiment is not low enough in order to reach this minimum, we could actually be fooled by seeing t-square dependence in this case as well. But I will come to this in a moment. Let's first look at the measurements. So we've done these measurements for niobium-doped bismuth selenide. You can see here the penetration depth dependence. It is clearly a t-square dependence. Pay attention to the axis down here. And so we could take this as an indication of point nodes. However, even though we are measuring to quite low temperatures compared to the superconducting transition temperature, you could still argue that since the minimum is expected to be very low, we are not reaching low enough and we are fooled by this t-square dependence. And in order to exclude that, we actually conducted proton irradiation of our samples. So what does proton irradiation do? Proton irradiation induces scattering in the samples, and it will actually weaken the superconductivity and reduce the superconducting gap amplitude. However, it would do that differently for different gap structures, and that's due to the following reason. For the point node system where we have symmetry-protected point nodes, these symmetry-protected point nodes, of course, have to stay. So we will only reduce the amplitude, but we will not change anything to the structure, so we will still expect to see t-square dependence. However, for the minimum case, which are not symmetry-protected, this additional scattering in our sample will wash out the superconducting gap structure, and while we reduce the overall amplitude of the gap, we will wash out the minimum, we will lift it, and might thus see a change in the low temperature dependence of the penetration depths. So let's have a look at the measurements. So we've actually simultaneously, while irradiating our TDO sample, we've also irradiated a transport sample. And you can clearly see by the increase in resistance here and the reduction in TC that we're doing quite some damage to our samples. However, if you look on the penetration depths, these does stay t square. So we think there's some clear evidence for also the realization of the delta 4x gap structure with point nodes in our samples. Okay, well, so having excluded conventional sources and thinking we know that this type of gap structure is realized in our systems, there's one thing which is puzzling for everybody working in this field so far, and that is the fact that in almost all measurements, there's no observation of domains. Well, why? So why would you expect domains? Well, of course, we have a trigonal system, so it has 3 equivalent axes. If this twofold gap structure has a preferred orientation, it should still pick one of the 3 axes at random. And of course, you would also expect it to form domains. So instead of measuring in resistivity samples this very nice twofold symmetric shape, why don't we see something that looks actually more like this, which would be an average over multiple domains with these gap structure pointing in along 3 different directions for each domain. Now, that is the one thing. The second thing, even though we don't see any domains, what people also report in all different kinds of experiments is that if we warm and cool the sample multiple times through the superconducting transition, not only don't we see domains, but also the same orientation of this preferred axis is picked each time we cool again through the superconducting transition. So it doesn't look like it would pick it randomly, but it looks like it has already a preferred orientation. And in order to investigate more in this, let me come back to the experiment I showed you before. So this experiment where we took a large strontium bismuth selenide crystal and we cut 2 samples at 90 degrees from each other. We've put them next to each other, as I told you, and measured these lobes here. And I just want to point out they're not only pointing along different directions, but if you look a little closer, they're actually related by almost exactly 90 degrees. So if I were to take this and put them here, you would actually realize that the maximum and the minimum HC2, or the nematic direction, is actually already given in this large crystal piece that we had here. And cutting these two crystals from this large piece did not change anything to the nematic axis. You might say this might be coincidence. However, I've repeated this experiment with another 4 sets of samples, and they all show the same result. So it looks like somehow in this crystal, there is already a preferred orientation. Now, why is that the case? Maybe there is some strain in the sample that's already coming during the growth. Maybe the intercalation is not uniform, making the nematic axis align by preferred direction. So we asked ourselves whether we could actually change this nematic axis by counteracting this supposedly internal strain of the sample. Now, since I might be the probably only experimentalist in this room which has never touched one of the strain devices, we've actually at Argonne conducted a very poor man's experiment of trying to change the nematic axis. I'm nevertheless showing it now to you. So we've taken 2 crystals that were cut with the same procedure, 90 degrees away from each other, and mounted them. We've measured those upper and lower critical field maps, or in some sense the high and the low resistance maps. You can see they're related by 90 degrees. We put them next to each other, and we actually mounted them on a glass fiber reinforced plastic. Now, what's special about these glass fiber reinforced plastic is that they have a very anisotropic thermal expansion along 2 different directions. So you can see here thermal expansion measurements that have been done in the group of Christoph Meinges at KIT. So you can see it has a low contraction direction and a very high contraction direction, and they're actually different by a factor of 3. And so if you were to mount your samples on here, they would experience a very anisotropic strain along one and the other direction. Now, comparing actually with the thermal expansion of strontium-doped bismuth selenide that you can see here on the right, you will actually come to realize that the thermal expansion of strontium-doped bismuth selenide matches quite well the low contraction direction of the glass fiber reinforced plastic. So we will treat this as almost uniaxial compression along this other direction. So for the 2 samples that we mount next to each other, you see here indicated the direction in which they will be actually compressed, since they are glued on this glass fiber reinforced plastic. And if our sample were to follow the substrate perfectly, we could expect a maximum strain of about 0.6% due to the mismatch in thermal expansion. Now we've done this experiment, and you can see here we've remeasured these constant temperature field in the plane sweeps, and you can see directly that we observe no change of the nematic axis in both cases. And of course, we could ask ourselves now whether we are actually applying strain. Are we straining our sample? And I think the answer is yes, because we've also measured the transition temperature, and you can see a clear reduction of the transition temperature, at least for this one sample. Interestingly, there is no reduction in transition temperature for the other sample, and we've conducted a second set of samples, and they show the same result. And the reduction in transition temperature is only when we have compressive strain along the high HC2 direction, and we see no change for compressive strain along the low HC2 direction in both sets of samples. Now, this either tells us that with the strain that we are able to apply, we're not able to counteract the internal strain of the sample and switch the nematic axis, or maybe there's a totally different mechanism at play in these samples here. So with this, I would like to conclude my talk. So I hope I have shown you that we have rotational symmetry breaking in the superconducting state of these doped bismuth selenides, whereas the normal state is shows no anisotropy. We have evidence collected that the delta 4x state in these systems is realized. And we think that there is a strong predetermination of the nematic axis in these crystals. And by strain, by gluing them on glass fiber reinforced plastics, we were not able to switch this nematic direction. I would like to thank you for your attention.